Welcome to the first video of Chapter C. We're going to cover two sections in one, again, just like we did the other day in class. And we're going to be focusing on perimeter and area. Now, these two topics should really be reviewed from who knows how long ago we're talking here. You know, when you guys first did perimeter and area, maybe 5th grade, 6th grade. So a lot of this stuff should be reviewed. We'll dive into some deeper stuff, but for the most part, this should be a pretty easy section here. First off, perimeter. We usually designate perimeter with a capital P, okay? Capital P, emphasis there. And perimeter is just the sum of the distance around really any polygon, where a polygon is a closed shape with straight sides, like a square, a triangle, rectangle, pentagon, hexagon, etc. Now, a circle is not a polygon. It does not have straight sides. But a circle does have a perimeter. It's just called something else. And we'll get to that next semester when we focus primarily on circles. An area is the amount of space in square units, whether it's square inches, square centimeters, square miles, whatever the unit may be, that fits inside any shape. Now, this doesn't have to be just polygons. So notice I did include a picture of a circle here. We can talk about area. And we designate area with a capital A. Surprise, surprise. Now, if a square has side length of s, okay, so unknown variable length s here, then what would the perimeter be? Well, if a square has 4 congruent sides and each side is s, well then s plus s plus s plus s would be 4s, would be a fast way of writing it. Okay, so nothing terribly tricky here. Then if we started talking about a rectangle, well, a rectangle is going to have a base b and a height h. Then what would the perimeter of it be? Well, we've got two bases, right, here and here. So there's 2b. So p equals, perimeter equals 2 bases plus 2 heights. So 2b plus 2h. And then if you really wanted to get fancy here, you could factor out the 2 and say the perimeter is 2 times the quantity, base plus height. Either way is fine. I typically just stick with 2b plus 2h. Areas for squares and rectangles use the same formula. It's just base times height, your length times width. Okay? Some of you know it more so as length times width, that's fine. Or if you want to call it base times height, that's fine. So base, height, area is base times height. Now for a square, the base and the height are really the same value. So you could call the area of a square b squared or h squared, or I still just call it base times height, and I just note the base and the height the same number. Now, we're going to talk about a parallelograms area. But first I start with a rectangle. So I have a base of 5, a height of 3. So the area of my rectangle here would just be base times height, which is 15. Now you might ask, well, where's the parallelogram at? Well, what if I drew a line, kind of slashed this corner, detached this corner, and stuck it over here on this end? Have I really gotten rid of any area from this original rectangle? And the answer is no. I've just taken some of the area and relocated it to another spot of the shape. This still has the same area of 15. The only thing that looks a little different now, this is still 5 up here. That still works. But the 3 isn't what you would probably call the height, because you might consider this slanty side. That used to be kind of what our height was now. But now it's just this part, okay? So the parallelogram area is still 15, which means we're still going to use the same numbers, the 5 and the 3. Here is one important thing to note. Let me jump back here. The base and the height of any shape are always going to be perpendicular. Okay, so if you can locate the base and you could locate a 90-degree angle or put one in, then the other piece that's adjacent to the 90-degree is going to be your height. Now a parallelogram is really just a tilted rectangle. Okay, imagine you have a rectangle and then we come over here and go, let me push you over a little bit. It's still the same shape, okay? It's just leaning over a little bit more. So since a rectangle and the parallelogram are kind of the same shape, then they must have the same area. So they're both base times height. Just keep in mind that in a rectangle, here's a 90-degree angle in a rectangle, so that means that piece and that piece, these two sides that are adjacent to the 90-degree angle, those are the base and height. Now in a parallelogram, we need to drop down a height to make it perpendicular. Okay, so that would be our height, and then this overall bottom piece would be our base. Now for triangles, the heights can be located inside, outside, or it could be an actual side of the triangle. All right, so let me just highlight these few instances here. So here's where the height is inside the triangle. And again, notice, here's my 90-degree angle, and look what is adjacent to it. The height makes up part of that 90-degree angle, the base, the other adjacent side. In this case, the height, if we have an obtuse triangle, then our height is really located on the outside. Okay, we just drop it down from a vertex down to, if you think about the same level as our base, and there's our 90-degree. Again, what's adjacent to it? The height and the base over here. And then if we have a right triangle, then this is our easier case to examine. Here's our right angle, what's adjacent, base and height. Okay, so just keep in mind the height in triangles can be in one of three different places. So the area formula for a triangle. Again, this is old school stuff here, but let me show you why you might know it's base times height divided by 2, or I refer to it as 1/2 times base times height. Okay, now here are a couple reasons why it's 1/2 base times height. Imagine here's my triangle, here's my base down here, here's my height. Well, I could take a copy of that left side of that triangle, flip it around. I'm going to take a copy of this triangle over here, flip it around, and then look what I've created. I've created now a rectangle, and the area of this rectangle is base times height. Well, how much of the rectangle is the triangle? It's half of it. Here's 1/2 of the rectangle, my original triangle. Here's the other half that I recreated. So we don't need that now. Throw it in the recycle bin. Now another way to look at it is, again, here's base, here's height of this triangle. What if I made an exact duplicate copy of that triangle and stuck it right there? Now what shape do I have? I've got something that looks like a rectangle, but it's tilted over, so it's a parallelogram. Again, here's the base, here's the height, there's my natural 90 there. So now I have two triangles. So this represents two triangles, and two triangles makes up one, we can say rectangular parallelogram. So if I want to solve for triangle, I could divide both sides by 2, and triangles equal 1/2 of a rectangle, or, try to make that tilted a little bit more, a parallelogram. So we can kind of look at it algebraically as well. Now another thing I want to show you here is with Geometers Sketchpad real quick. So notice I've got a triangle, here's my height, here's my base, and I've got it set right now so the height is 8 centimeters and this base is 10 centimeters. All right. Notice that the area would be 1/2 base times height, so base times height divided by 2 gives me 40. Now I can take this triangle and slide it around. I can really stretch it out. I could make it not stretched out at all, kind of make it look like it's more isosceles. But notice the area is not changing at all. Notice the base, I'm not really stretching that, and I'm not really stretching the height. The height is this dotted line here. So the base and the height are staying the same. I'm just really stretching out the area so that it's still the same value. Okay? Now just to show you that things really can change in this problem, I'm going to lower the height down to now say 6. Okay? But again, if I stretch this thing out, notice nothing's moving. The height still stays 6, the distance between these two parallel lines. The base is still 10, so the area stays constant. It stays 30 that entire time. Okay, so I can have a triangle over here that looks really obtuse. I could have one that looks isosceles. I could have one that looks like a right triangle. But all of those triangles are going to end up having an area of 30 if I leave the height and the base alone. So you can stretch that thing out. It looks different, but it's not really different. All right, now this part's not in your notes, so please add this to the very bottom here. And this is a really short ditty on how to find the area of an equilateral triangle. Okay? There's a little formula here I'm going to throw at you, but I also want to explain how can you really do this. Well, an equilateral triangle just means all three sides are the same value. So we'll say in this example they're all 10. Now, this could be my base of 10, but the height would have to drop down from this vertex straight down and make a 90-degree angle. And this height is currently unknown. Well, how could we figure out that height? Here's one thing to notice, that since this is equilateral, and if I drop down this height, it splits the equilateral into two right triangles. I got one over here on the left, one over here on the right. And what do you think is going to happen to this 10 down here when I drop down that height? Well, it's going to split it into a 5 and a 5. And now we're going to put all of our focus on one of these right triangles. Because right now I've got a right triangle, and I know two of the sides. This side down here is 5, and this piece right here is 10. And so I'm going to use the Pythagorean theorem to solve for the height. Now my C side is going to be my 10 here. I'm going to call the height my A and the 5 my B. So if I do A squared plus B squared equals C squared, A squared would be H squared, B squared would be 5 squared, and C squared would be 10 squared. I have H squared plus 25 equals 100. Subtract the 25 over, and I get 75. To get rid of the square, I'm going to square root both sides. And now to simplify the square root of 75, I could do 25 and 3. The square root of 25 is 5. So the height simplified would be 5 root 3. So now I can write that value in. There's 5 root 3. Throw this up, throw this over here. So now if I wanted to find the area of that triangle, area is 1/2 base times height. Well, now I've got 1/2. The base was 10, and the height I just figured out was 5 root 3. So now if I've got that, let me slide you down. Let's just get rid of the Pythagorean theorem altogether. There we go. 1/2 of 10 is 5, and 5 times that 5 makes 25. And 25 root 3 feet squared would be the area of that equilateral triangle. Now you can do that every time, but there is a pattern involved here. Okay? And this pattern is not quite so obvious as what you might think it is. So I'm going to throw a formula out here at you. The area of an equilateral triangle is equal to the side squared. That's not a 5, so I'll put side. Side squared times the square root of 3 all over 4. That will work every time for an equilateral triangle. So let's just try it again real quick here. Side squared, well, my side was 10, so I'd have 10 squared root 3 divided by 4. Well, 10 squared is 100, root 3 divided by 4. I can simplify this part, because those are actual whole numbers that aren't square roots, and 100 divided by 4 is 25. I drop down the root 3, and there's the same area that I got before, just a lot faster. So you can use this formula if you like for equilateral triangles, or if you forget, you can always just drop down a height. There it makes a perpendicular, it splits the bottom base, and you could just use the Pythagorean theorem to solve for the height to calculate the area. So that's a little extra part there. First example says you have a swimming pool that is 12 by 20 feet. All around the pool is a 5-foot wide sidewalk. How much fencing is required to go around the sidewalk? Okay, so here's where we want to put the fencing, is around the sidewalk here. So are we talking about area or perimeter? Well, since we're only talking about outside length here, we're talking about perimeter. All right. Now, if this much on the pool is 20 feet, how much extra do we have to add on here? And that would be 5 feet. How much extra would we have to add on over here? That would be another 5 feet. So this whole thing would be 25 and 5, which makes 30 feet. Which means we also need 30 feet up on the top part. Now, for the vertical pieces here, this much we said was 12 feet. This much extra is going to be 5. This piece down here is going to be 5. So we're adding on 10 to our 12. So this whole thing over here is going to be 22, which means the whole thing on the right side is 22. So the perimeter is going to be 2 30s plus 2 22s. So we got 60 and 44 gives me a perimeter of 104 feet of fencing. Second example, calculate the area of the parallelogram. So first you're thinking, all right, parallelogram, that's easy. Base times height. There's base, there's height, there's that 90. So yeah, those are the base and the height. So 6 times 6, that makes 36. And then when you go to write down the units, you might just look down here and go, hey, this is in feet, so it's feet squared. Some of you might not look at the base and go, hey, look, that's yards squared. Wait, yards and feet. Wait, that's not the same unit. So the answer's not 36? Oh, well, here's what we could do, right? We could just say it's 36 feet yards. Quantity squared? Something like that? No. Everything's got to be in the same unit. So there are 3 feet to 1 yard. So which way could we do some converting here? Well, actually, in this case, you can go either way. So you can call 6 yards, really that's 18 feet, and 6 feet would be 2 yards. So you could write your answer one of two ways, in feet squared or yards squared. It really doesn't matter. So if we did feet squared, well, we had 6 feet for a base, 18 feet for a height. That's going to give me, what, 18 times 6, 108. Feet squared would be one answer. And another would be if we want to do it in terms of yards. So the base was 2 yards, the height was 6 yards. So we get an area of 12 yards squared. Both of these answers are technically the same. It's just different units. So whatever way makes more sense to you, go for it. Now, one extra thing I want to talk about here is notice the difference between these two answers. We said there are 3 feet in 1 yard, but notice the difference between these answers isn't just a times 3 factor, right? If I took 12 yards squared and multiplied it by 3 feet, that only gives me 36 feet. So why is this answer 108? You see what I'm saying? If I multiply 6 by 3, I get that. If I multiply 2 by 3, I get the 6 feet. So why can't I just take my answer and multiply it by 3 as well to get the answer in feet squared? Well, the answer lies in that we can't just multiply this by 3 because we multiplied by 3 technically twice. So if we multiply by 3 squared, times 3 and another times 3 makes 3 squared. And what is 12 times 3 squared, aka 9? 108. Okay? So anytime you want to do some conversions that are in square units or cubic units, you need to make sure that you multiply by whatever the linear factor is. This is what you would call the linear factor. You need to multiply that or really take it to the power of whatever units you want to be in. Okay, so just keep that in mind. It's not, you can't just easily convert your answers by multiplying by the same thing as you did with your linear conversion. All right, some other conversions that I hope to goodness you guys know. Definitely, we just talked about this one. There are 3 feet in a yard. There are 12 inches in a foot. Then metric, sometimes we'll use some metric stuff, but there are 100 centimeters in a meter, which I'm sure most of you remember. This is the one thing that maybe I only get about 5 people remember how many feet there are in a mile. And it seems like such a random number, but it's 5,280 feet in a mile. You definitely want to remember that one. All right, 2 more examples. Calculate the area of this looking shape. Well, this kind of looks like a trapezoid, but we haven't talked about trapezoids. So how can I really find the area of a trapezoid when we haven't talked about it? Well, notice what they've kind of done here for you. They've split it up into 2 shapes. We got this shape over here, which kind of looks like a parallelogram. And we got this shape over here, kind of looks like a triangle. So we're just going to split this thing up. So over here they said this piece is 21, This piece up here is 15. Now that 15 that's right up here, yep, that's what I figured. Detach you. Can I take you now? Oh, I can take you. We can take that 15 and just slide it down, because there's our 90-degree angle. We can say, all right, well, there's our 90. So this piece that's adjacent to it, that's the base. This piece adjacent to it, that's the height. So the area of our parallelogram is just 15 times 21, which makes 15 times 21, 315. And I'm in the same unit, centimeters and centimeters, so we're good there. No conversions. Then when we get to the triangle, we're going to have to take 1/2 base times height. Well, I can see the base down here. I could call 20, but the height, I don't know what that is. They didn't give it to me, but they kind of did. You just get to use the height over here, the 21, and slide it over, and think about it as still being 21. So if we do base times height, 20 times 21 divided by 2, that'll give me 210 centimeters squared. So now add everything together, and we get a total area of 525 centimeters squared. So bigger shapes, just break them down. And the last example, I'm going to leave this one for you guys to do. Okay? There's kind of two parts to it. It says your baby's daddy wants to lay some new hardwood flooring on the first floor of your house. I mean, it's only the nicest thing he could do, right? Besides raise your child, is to, make upgrades to your house. Sure. So how much flooring, this is question one, how much flooring is needed based on the blueprint? Okay. How much flooring? So you need to figure out, is that a perimeter and area type answer you're looking for? And then question number two is, how many linear feet of baseboard is needed to go around the room? Now, some of you may not be familiar with what baseboard is, so let me just describe it to you pretty quick. If you ever look down, and even if you look around the classrooms, there's baseboard technically. Baseboard is what kind of covers up the little space between the floor and the wall. Okay, if that wasn't there, you would see probably a little crack or crevice going all the way around your room. That's where the drywall comes to meet the floor, but it doesn't always make a flush setting. So you buy baseboard, and baseboard just goes around the edge of the room here. Okay, it kind of hides any little flaws that may have happened in the building process, if you will. So it just goes all the way around like this. Not so thick there, but I think you get the idea. If you look at your house, I guarantee you have baseboard. So that's what I'm looking for there. So how much flooring do you need, and how many linear feet of baseboard do you need to go around the whole room? Now, one thing we are assuming here is that there's no doors. Obviously, if you have a door, let's say right here, you're not going to need baseboard to go by the door. So ignore any kind of door factors here. There might be multiple doors, like we need to go in here. Now this is the kitchen area. So just assume there's no doors. We'll just kind of leave that part out of it. And all of these units, I didn't really put any units. If it was feet, this would be one crazy huge room. So I don't know. I'll just leave it open. We'll just call them units. Okay? And that is all for your first video.